Hello, welcome to 13 Universal. We are still on A-level CI biology and we are on paper 5 planning analysis and evaluation series 6. This is Shedro. So get your materials. Let's solve some questions. Remember, we solve the questions together. So you pause the video once the question is read and then you try to solve it, okay? So come on, let's go. It's time to apply some concept. Let's fry some fishes, guys. Now, the first question. Remember, the way this comes is that the background information is usually a lot. Okay, this is very worded and it is deliberate. So it is deliberate because they are testing your ability to be able to understand a new information, okay, new context, unfamiliar context, and then apply what you know in this unfamiliar context. But you have to understand it first and then remember what you're reading. So I always advise students to do immersive reading. Okay, let's go. So there are a variety of methods used in to estimate water potential of plant tissue. So this is all about estimating water potential. So from beginning, you know what you're doing. Okay. Now, it says a student decided to estimate the water potential of potato tuber tissue using method described. Okay, this is the method described. Let's go, guys. A number of test tubes were set up, each containing the same volume of sucrose solution. Okay. Each test tube contained a different concentration of sucrose solution. So they have different concentrations of sucrose solution. So you have to be interpreting what they're saying. All right, pieces of potato tissue were placed in each test tube. After a period of time, the potato tissue was removed from the test tubes, so they removed it. The student then measured the change in density of sucrose solutions left in each test tube. That's when the pieces of potato tissue, were removed. So for each of those test tubes, they now determine the density, right? Change in density, whether it increased or decreased. The water present in a sucrose solution, the less dense it is. So the more water in a sucrose solution, the less dense it is. Okay, the more water present in a sucrose solution, the less dense. Do you understand this? If it has more water, that means water would have moved into the potato tissue. It would have lost water because water moves into potato tissue. If it has more water than potato tissue, it moves in by osmosis, and then we have less water. Okay, and the sucrose, yeah, if you have more water left, look at it. The more water present in a sucrose solution, that is after you have removed the potato tissue, if you have more water left, so it's going to be less dense. But if you have less water left, it's going to be more dense. Okay, sugar solutions of the same concentrations as those of the original test tubes were prepared. Each of these sucrose solutions was colored with methylene blue. One drop of the colored sucrose solution of a known concentration was released into the middle of the test tube. Okay, so you follow it. Whose sucrose concentration was originally the same as that of the colored sucrose drop. So we have sucrose drop. Okay, so when you remove the prepared under solution, you can see that, right? And then put a drop of methylene. Okay, the three possible outcomes that the student would see are shown in Fig 1.1. The drop will rise if the colored sucrose drop, so we have colored sucrose drop, is less dense than the sucrose solution in the test tube. It will rise. The drop will remain where it is released if the colored sucrose drop is similar in density to that of the sucrose solution in the test tube. So it remains the same level. The drop will sink if the colored sucrose drop, okay, so we have colored sucrose drop is more dense than the sucrose solution in the test tube. Okay, these are the instructions. So you have to pay attention to them and remember what I've said. Let's go to the next page. Okay, identify the independent variable in this experiment. So the question is, what are we changing? So independent variable is what you're changing. So pause the video and write it. Okay, what are we changing? Okay, so what is being varied here? Pause the video and try it. Different concentrations of sucrose, okay, in different test tubes. All right, so different concentration. All right, yeah, we're going to look at it later. We'll look at this. Okay, this is um, the diagram trying to explain what was said. So point of release, that means the colored sucrose drop is less dense. Colored sucrose drop is the same, all right, same water potential as this. Colored sucrose is denser, that's why it decreases. Okay, so let's look at that answer there. Identified independent variable. Okay, concentration. Okay, or water potential of sucrose solution, because the concentration is affecting water potential. All right, so concentration, we have different sucrose concentration, that's what we're changing, right? Okay, so let's go to the next question. Predict the result if the water potential of potato tissue was higher or less negative than the surrounding sucrose solution. Okay, so I want you to pause the video and try to solve it. Pause the video. All right, so remember, if we have something like this, look at this. Okay, right, because, and then this is potato tissue placed in it. All right, okay, so let's see what happens. So it was submerged, all right, in this sucrose. This is sucrose sucrose solution. All right, so this was submerged there, this potato tissue submerged. Then they said predict the result if the water potential of the potato tissue was higher than the surrounding tissue. If the water potential here is higher than the sucrose solution, right? So what would happen? Remember, if it was higher, so water will always move from region of higher concentration to lower concentration. Okay, so how would water move? Water will leave tissue, potato tissue, into the, all right, into the sucrose solution. So water will move out of the tissue and by osmosis into the tissue. And then when water moves out, it dilutes this sucrose solution. So now it has more water than before, so it becomes less dense. So by the time you drop the colored sucrose, put this colored sucrose drop in this, all right, solution, it will go down. It will go down because this solution has more water now, so it's less dense than the colored, all right, sucrose drop. Why does it have? Why is it less? Why is it less dense? Because water already moved into it from the potato tissue. Do you get? Okay, so look at it. So colored sucrose drop would sink. It will drop or sink. It will go down, right? Because this has more water. Water has left tissue, potato tissue into the sucrose. Okay. The next question: explain the prediction that you gave in AI. Now, pause the video and try it. So why would it sink? Why would the sucrose, color sucrose, drop sink? Why would it sink? Right, it will sink because water moved out of potato tissue into the sucrose solution, and then sucrose solution becomes less dense. Okay, therefore the color sucrose sinks. Okay, so water leaves potato by osmosis, sucrose solution becomes less dense. Right, so anytime they say explain, give us reason. Right, that's 2 marks. Right, now look at another background information. The student then used another method to estimate potential water potential of potato tissue. There's a water potential here. Okay, so the student placed pieces of potato tissue in a range of concentrations of sucrose solutions. The equivalent sucrose concentration was identified as a concentration of sucrose solution in which the potato tissue did not gain or lose, all right, lose mass. The equivalent sucrose concentration indicates the water potential of the potato tissue. Okay, because it has the same the same water potential with the potato tissue. The net movement of water is zero. Okay, that's why it didn't change. Okay, increase in size. So that particular sucrose solution would have the same water potential as the potato tissue placed in it. So question I, the student was given a stock solution of sucrose with a concentration of 1.0 mole per dm cube from which to make a range of dilutions. The student decided to make 20 cm cube of each concentration of sucrose solution, 20 cm cube. Describe how the student prepared 20 cm cube of solution with a concentration of 0.4 mole per dm cube. So if you have been following our videos, you should be able to solve this, okay? But meanwhile, pause the video and then describe how the student will prepare. All right, 20 cm cube of the solution with a concentration of 0.4. So don't forget that. Pause the video and try it. Now welcome back. Now look, this is it. Okay, this is the first one, which is 1.0, okay, per dm cube. That's the first concentration. So this is second concentration, which is 0.4 per dm cube. That's 0.4. I'll just write 0.4. Okay, so we want to use 1.0 to produce 0.4. Okay, so this is initial concentration. That's my C1. Okay, now this is the final concentration. That's the C2. So C1 is the concentration you are using to produce another concentration, okay, or the concentration of the stock solution. Do you get? Now remember that they told us to prepare, of course, 20 cm cube of 0.4. So that's my V2. When you have added water to it, everything you have, all right, should be 20 cm cube. So 20 cm cube is therefore the final volume. We call it V2. So for us to be able to prepare this 0.024 mole per dm cube, we need to dilute the 1.0, all right, mole per dm cube by taking part of it. So we'll take a particular volume of the stock solution, put it in a beaker, right, and then to it take a particular volume of water. Okay, so you need to know the volume of water you are taking, right, because you are diluting. So in dilution, we're adding water. Remember, we're adding water to a particular solution to dilute it. So we're adding water. So what's the volume of water we're adding? So this is V1. V1 is the volume of the stock. Okay, so we need to know what V1 is. Don't forget that our V2, which is final volume, is equal to, okay, the volume of stock, which is V1, okay, plus volume of water. So because we're adding water to V1 to dilute it. So but when we add water to V1, our total volume of adding two of them, they should make up to V2. And in this case, our V2 is 20 cm cube. All right. So let's get our V1. Don't forget the dilution formula. That's C1, all right, V1 equals to what? Equals C2 V2, all right? C2 V2. That's very important. C2 V2. So everything has been given. You just need to get V1 so that we can get volume of water. So V1 will be what? It will be equal to just making it of the formula C2, all right, V2, all right, that's dilution formula. Okay, yeah, that's V2. Okay, all over C1. So our C1, all right, is 1.0. Now C2 is 0.4. All right, get your calculator. Let's do this. 0.4 times what? Times V2. V2 has been given to us, which is 20. So you multiply 0.4 on 20. You get? And then you divide by 1. Divide by 1. Okay. Yeah. So 0.4 times 20 should give what? Should give you 8 cm cube, all right? So my V1 is actually 8 cm cube. So I have to take 8 cm cube of the stock concentration and then add how much of water to make it 20. All right, to get the volume of water, okay, so you see the volume of water here, you already know your V1. We've calculated our V1. V1 is 8, right? So volume of water will be what? Okay, it will be V2 minus V1. V2 is 20, all right? Yeah, V2 minus V1. So 20 minus 8 is what? 12. So if you say 20 here, all right, which is V2 minus 8, that gives you 12. Is that okay? Yeah. So this gives us 12. So we are taking 12 cm cube of water. Okay, mixing it with 8 cm cube of, this is 12, sorry, 12 cm cube of water. We're going to mix it. Okay. So we'll take V1, which is 12 cm cube, all right? So how they say you should describe this. Describe how. So all you just need to do is take 12 cm and 8 cm cube of the stock concentration. Stock is 1.0 mole per diem cube, all right? To take 8 cm cube of it, okay, put it inside a beaker and then add 12 cm cube of water to it. Okay, so once you add that 12 cm cube of water to it, they will make up 20 cm cube of 0.4 mole per diem cube. All right, so take this, put it here, add this, it will make up 20 cm cube of 0.4 mole per diem cube. Okay, that is the answer. Okay, see the answer. Add 8 cm cube of stock solution with 12 of the seed water. Remember, you must have to calculate it. When they give you final volume, you have to calculate your initial volume, right? But if they don't give you a final volume, just say they take a particular amount of stock solution, add water to it, okay? But if they give you final volume, you have to calculate your initial volume. So it now states specifically how much, the V1 is how much of the stock solution you are taking to dilute. You cannot dilute everything here. Okay, so that's it, guys. Now, the student carried out a risk assessment before carrying out the experiment to find the equivalent sucrose concentration. Okay, so risk assessment. So just one reason why student decided the level of risk for this method was low to medium. So risk assessment has to do with hazard. You know what hazard, what can actually pose danger to students here. You say any chemical that can pose danger. So you know, one reason is to identify the hazard, okay, and then the risk of the hazard is very important. The risk of the hazard is what the hazard could do. For example, if it's sucrose could be an irritant. Sucrose solution could be an irritant to some people. All right. Now, potato could actually be an allergen to some people. So, potato is a hazard. Why the allergy or allergic reaction is the risk? Is that okay? We need to find out. All right. So now you need to know hazard, okay, and the risk, and that will help you to know the precaution you're using. All right. Describe a method using measurement of mass. So they're giving us that the student could use to determine the equivalent sucrose concentration in the potato tissue. Okay, now this is method. Do not include details of how to make different sucrose concentration or the risk assessment. Use method. Your method should be set out in a logical way and be detailed enough to let another person follow it. This is very important. Okay, so this is about 6 marks or thereabouts. Okay, I've said it because you're going to write a prose, an essay, structured essay that is very descriptive. Okay, but you have to have an outline to be able to do that. So in your outline, you have to identify your independent variable here, and how to vary it if you are not asked not to talk about how to vary it. All right, our independent variable here, sorry, is the sucrose concentration, and how you vary concentration is by dilution. So they say we should not mention, all right, we should not mention how we determine the sucrose concentration. So we should not mention it. All right, so all right, so another thing you have to is dependent variable. Dependent variable is your sucrose, your potential. All right, water potential. But how you measure water potential is by measurement of mass. Okay, how are you going to measure change in mass, right? So of course, remember that you're going to put the potato tissue in each of the sucrose concentration, okay, because what you do here is measure. Dependent variable we measure. So as you're planning to start writing, this is your outline. You are getting ready. It's an essay. So how are you going to measure this? So you know that, okay, I'm going to have mass before inserting in sucrose solution, and then mass after, all right, a particular time. All right, so you know you have the key variables, which is standard variables. What are you going to keep constant? the size of potato, the mass of potato, the age of potato should be kept constant. All right, the volume of sucrose concentration should be kept constant, temperature should be kept constant, and of course, that's very important. And every other thing, okay, the constant variable that could affect that experiment. So you now have to, all right, reflect and retrieve what should be kept constant before you start writing. This is your outline, and then you have to think about reliability. How do I ensure reliability? Reliability is by repetition. Okay, so reliability is by repetition. Repeat three replicates and calculate the mean. Okay, you have to mention it. Then you now talk about the risk factor, hazard, and all of that. Which one is it, and all of that, and then mention it. But don't say I determine that. Okay, so and then precaution. So if I want to start this, I just mentioned, of course, that same volume of, just you're writing, okay, start writing that same volume of different sucrose concentrations, okay, were put in test tubes, okay, same volume. And then, of course, you now talk about the potato, that the potato mass were potato tissue cut out using scalpel, all right, and they have the same dimension, the same size. Okay, so the potato tissues put inside the different sucrose solutions, and they're allowed. All right, now before you put it, please, it's very important, before you put it, you said these potato tissues, all right, they have stated mass, so they must have measured stated length, and then they now are immersed in the sucrose solution and allow for some minutes. After some minutes, they are removed and then blot the potatoes sucrose solution on them, all right, blotted out, and their new mass is reweighed, and then change in mass is calculated. So the one that has no change in mass, okay, has the same water potential as sucrose solution. Okay, so you can mention that for reliability sake, you have to do replicate value, three replicate value, and calculate the mean, and then the hazard there. So look at it, guys. So you see, this is the bullet point. What it's supposed to say. It's simple, guys. It's simple. Use minimum of different concentration of sucrose. Okay, five different concentrations. You can state it. Five different concentrations. You can state it there. All right, from one. If you have one mole per DM cube, you could have 0.8. Okay, all right. You could also have just same interval 0.6. All right, okay, but we're not going to describe how we prepare them because they say we shouldn't bother. 0.4, but you could state them. Okay, all right, 0.2, 0.4, 0.2. Okay, now the second point there says method, all right, of measuring, because you have to state method. So method of maintaining what temperature. Okay, same temperature. Yeah, so use water bath, statically control water bath. Okay, use same type of age of potato. All pieces of potato are the same, stated the dimension. Method of to create potato of a certain dimension, use ruler and scalpel. Method potato pieces are fully covered, submerged, so they are submerged by sucrose solution. Removed after same time for all of them. Measure the mass of potato before and after. Method of drying, okay, blot it out, calculate the final, okay. Repeat the experiment, and then all right. So the one that has okay, the blend sucrose change in mass has okay the same um water potential. That's 6 marks, guys. The student um, the student determined a value of 0.46 mole per DM cube for equivalent sucrose concentration of the potato tissue. Use Fig 1.2 to determine the water potential of the potato tissue. Okay, that's it. Yeah, so guys, you know how we do it. This is your x-axis, this is your y-axis. Determine the value of one box. So for this x-axis, which is sucrose concentration mole per DM cube, what's the value of one box here? All right, now from here to here is 0.1, so 0.1 represent 5 boxes. Okay, so one box will be 0.1 divided by 5. Okay, so that will give you 0.02. Is that okay? So one box is 0.02. Is that okay? So we're looking for 0.46. So this is 0.4. So the next box is 0.42. The next is 0.44. This one is 0.46. Trace it down here. Okay, trace it down here where it touched this. Okay, let me mark it out. Meanwhile, you could pause the video and try it. Okay, so trace it down. Yeah, I think it should be here. This is where I touched it. Okay, the graph. Remember, okay, this is just like half of a box. Okay, trace it. It's just like half of, close to half. All right, of a box. Trace it here. But also we need to find the value of one box on the y-axis. Okay, find the value of one box. Okay, yeah. So look at this. Don't forget that here, from here to here is 0.5. So one box will be, 5 boxes gives us 0.5. One will be 0.5 divided by 5. Do you get? So that will be 0.1. So each box 0.1. So this is minus 0.1. Okay, then the next box will be minus 0, minus 1.1, and then the half will be minus 1.15. You get? That is the water potential if you follow this 0.46. Okay, so that should be minus 1.5. Is that okay? 1.15. Sorry. Okay, this is 1 minus 1.0 minus 1.1, so minus 1.5. All right. Okay, that's water potential. Yeah. So let's go to the next question. 1 mark. The students compare two types of potato. These are two types, record and Cai's pink, to see if there was a significant difference between the water potential of the two potato tissues. Okay, is there significant difference? So it's trying to do statistics test. The student decided to carry out a t-test. State one condition of the data that allows students to carry out a t-test. Now, pause the video and try it. So what are the conditions that allow for t-test? The criteria, guys. Remember, that's how we do. Pause and try. Pause video and try. Okay, P and T. Pause and try. All right. So what you do is that, okay, of course the data must be continuous. Okay, quantitative. All right, continuous data for you to use t-test. Okay, it must show normal distribution. Okay, and the standard deviation of the two population must be similar. All right, and they're using it to compare the means. Remember, t-test is to compare the means of two different populations. Okay, look at it. Okay, don't forget it. Anytime you're dealing with t-test, these are the conditions for using t-test. Data is continuous. Data is normally distributed. Don't forget it. In biology, our key is memory. You must remember things. All right. 3, comparing two means. So that's what we use t-test. And then the standard deviations are approximately the same. It should be approximately the same. Okay. And then it should be fewer than, all right, 30 values for each potato. It should be greater than 10, right? Between, right, 10, 30. Okay. So these are the criteria. State the null hypothesis for the test, for the t-test carried out. Remember that null hypothesis is a negative hypothesis. So null hypothesis will tell you, it will say there is no significant difference. Okay, there's no significant difference between the water potential of the two potato types, that is the record and Caie pink potato. Right? There's no significant difference between we're dealing with, okay, the mean, yeah, because we are dealing with t-test, yeah, the means of the water potential of the two potato types. No significant difference, all right, between them. So look at it. No difference between the water potential of the two types of potato. Okay, no difference. Okay, or no difference between their mean. Okay, the mean water potential. Okay, all right. Now that's 1 mark. The student tested 20 samples of each type of potato or potato. Calculate the number of degrees of freedom, V, for the t-test using the formula given. Okay, so what is the formula given? Yeah, that's the formula for degrees of freedom for t-test. Remember, if you are dealing with chi-squared, all right, the formula changes. That means v for this is for chi-squared, or anyway, it's going to be n minus 1, okay, for chi-squared. But this is for theta, right? Yeah, okay, and that is for chi-squared, right? So they all have degrees of freedom. Okay, so they say calculate the number of degrees. So you know that the two populations are 1, so this n1 is 20. Okay, so what it should be, I think there's the formula is wrong, there's a typo there, so it should be n1, okay, yes, minus 1. That's it. This is the real formula. Okay, there's a typo there. N1 minus 1 bracket plus, okay, yeah, so this should be bracket plus n2 n2. Okay, it's the same thing. No, it's not a typo. All right, it's the same thing, please. So either you do it this way, okay, yeah, it's the same thing. It will give us the same formula. Yeah, it's the same thing, guys. So this is 20. If you like, I can try 20 plus 20, okay, minus 2. Yeah, the same thing, guys. Sorry. Yeah, 20 plus 20 is 40, right? 40 minus 2 is 38. Just 2. So this will give us 38. Okay, so that's the degree of freedom, 38. Okay, if you decide to do this the same way, all right, 20 minus 1 is 19, right? So 20 minus 1 also here is 19. 19 plus 19 is 38. Okay, add 2 of them, each one is 20. Okay, so that will still give you 38. So that is 38 degree of freedom, 38. 1 mark. Okay, table 1.1 shows the critical values of t at 0.05 probability. This is critical probability. That's a table. Degrees of freedom, critical values of 0.01 probability. Okay, now the student calculated t as, so this is our calculated value for t. They say with reference to table 1.1, okay, and the calculated value of t, make a conclusion about the water potentials of the two types of potato tissue, record and Caire's pink. All right, so they say we should explain your reasoning, make a conclusion to explain your reasoning. Okay, now before you can do that, we have said it in former videos that there is a decision making, okay, pattern. The same for t-test, chi-square, and Spearman correlation, right? So if the t calculated value, t-test calculated value, right, is greater than t tabulated value, that's it. If this is greater than this, at probability, critical probability of 0.05, if this is greater than this, then it says reject the null hypothesis. Reject it. Reject null hypothesis. Otherwise, accept null hypothesis. So that means if it is less than that, then accept null hypothesis. But if it's greater than this, then reject the null hypothesis, right? The null hypothesis. Okay? The null hypothesis is written like this. Okay? The null hypothesis. Otherwise, accept it. Okay? All right. So now this calculated is t calculated value, all right, is 1.89. okay, 890. So let's check it out. Okay, the tabulated value, you have to use degree of freedom. We got is 38. Trace it. This is 38. Trace it here. So this is tabulated value, 2.024. So 2.024. The other one is 1.890. This is 2.024. Of course, you can see that the calculated t-test is not greater than the tabulated t-test at critical probability of 0.05. Okay, this is 1.890. It's not greater than 2. So if this doesn't work, that means you should accept the null hypothesis. Okay, so accept the null hypothesis, and therefore you state that there is no significant difference, because null hypothesis states that there's no difference between the means of the water potential of the two types of potato. Okay, say it. So critical value for this 38, and then this is 0.0, so that's it, 0.024. That's going to write it. Calculated t-square is this, so this is less than the critical value. Okay, therefore you accept null hypothesis. If it is greater, then you reject it. But once it's less than, you accept null hypothesis. And what does it state? There is no significant difference between the means of the water potentials of two varieties of potato types. Okay, all right, 3 marks. That's huge. Well, let's go to the second question, which deals more of evaluation. All right, and analysis. So respiration in blow fly larva, Califora erythrocephala, can be studied by determining the respiratory quotient, RQ. A student used the apparatus set up as shown in Fig 2.1 to measure oxygen uptake by blowfly larva during respiration. 5 replicates were carried out. So let's see it, guys. Come on. Now that's it. This is the diagram. Okay, the setup. This is manometer containing colored liquid. This is scale. This is the tube. Okay, this is cotton, substance X. Okay, yeah. So guys, let me ask you, how would you measure, of course, how would you measure rate of transpiration? Okay, sorry, rate of respiration. Okay, which is, how do you measure the amount of oxygen, whether the rate is high or low? How would you measure that? Okay, so pause the video and tell us, how will you measure the volume of oxygen? Right, volume of oxygen used up. Remember that this larva uses oxygen. Okay, uses oxygen. So remember that there's air here, okay, and there's air here. That air is exerting pressure. Okay, here. This also exerting pressure. This is atmospheric pressure. This is pressure, internal pressure here, is due to volume of oxygen. Okay, so by the time respiration starts, remember, oxygen is used, and then CO2 is produced, because respiration releases CO2, carbon dioxide, but carbon dioxide is absorbed by this substance X. Okay, so that means that oxygen is used up, CO2 is absorbed, the volume of oxygen here, the volume of air here decreases, the volume of oxygen here decreases. Therefore, the pressure here will decrease. It will be less than the pressure here. Okay, therefore the pressure here pushes the colored liquid, causing the meniscus to move upward. Okay, it moves upward because oxygen is being used for respiration. All right, and this moves upward. The pressure decreases, volume decreases, pressure decreases. Okay, pressure is now less than the atmospheric pressure, so it moves upward. Okay, so let's quickly look at what I want. State the role of substance X in Fig 2.1. But it's always good interactive diagram. Okay, the role of substance X. What is the role? Write the answer. Pause and write. Okay, this X is CO2 absorbent, so it absorbs CO2, removes CO2, because we're measuring first of all the amount, the volume of oxygen. Okay, and that's by the distance moved by the meniscus, right? Convert the distance to volume. So if you want to measure oxygen volume, you have to remove CO2, right? So that's this is KOH, right? Potassium hydroxide, removes it. Okay, all right, so let's see what is it. Okay, to absorb, remove, take up carbon dioxide produced during respiration of blowfly larvae. 1 mark. Predict which direction the meniscus in the manometer will move during the experiment. We have said it. It will move upwards. Okay, to move upward. Why? Oxygen is gonna be used for respiration, so the volume decreases, the pressure decreases also. All right, the colored liquid will move upwards, and as oxygen is taken up using expression decreases the volume and pressure of gas in the test tube. Okay, and that's why it moves upward. 1 mark. To calculate the RQ, the student determined the volume of carbon dioxide produced. Yeah, by the blow lava. Describe how the apparatus in Fig 2.1 was modified so that volume of carbon dioxide produced was determined. Now, if you want to measure, pause the video and try it. Okay, so how do you measure, how do you modify the apparatus to measure the volume of carbon dioxide? Try it. Okay, you know that X in that diagram removes carbon dioxide. Now we want to measure carbon dioxide, all right, volume. So you have to remove X and then replace it with an inert, all right, object like, plastic or glass beads. Okay, so that all CO2 is no longer being absorbed. So remove substance X, replace X in material, glass bead, and all of that. All right, state two variables that should be standardized each time the student carried out the experiment. Okay, state it and text it on YouTube. Send it. I want to see it, and I'll give you chocolate. All right. Of course, what could affect respiration there? Temperature could affect it. Okay, should be standardized. Okay, the mass of the lava, the age of the lava, right? The species should also be the same. Okay, of course the mass of that X should be the same for all of them. Temperature, number of, okay, I see number of blow lava, mass of blow lava, age of blow lava, food source of blow lava should be the same. Mass of number of, yeah, X. Okay, yeah, time to equilibrate, because you have to equilibrate so that the temperature of the blow lava will be the same. Okay, time to equilibrate should be the same. Time for measurement of meniscus. So time for example, once the experiment starts, you say, okay, we're going to measure the meniscus after 5 minutes. It should be the same, all right, for all of the setups. Table 2.1 shows the result and calculations made by the students. All right, look at that. See what the student made. Replicate distance moved by manometer field. Replicate 1. Volume of oxygen, right, for each of them. Replicate 1, 2, 3, 4, 5. All right, then I said the result for replicate 1 ringed circled, okay, in table 2.1 is anomalous. Anomalous means it does not follow the trend. Okay, it doesn't follow the trend. So this is anomalous. It's odd. Okay, suggest two possible causes for this anomaly other than measurement of error. So anomalous values are always introduced either by the way we measure vary the independent variable, or change it, or measure the, okay, the dependent, or or what we keep constant variable, these three. So here it could be maybe the constant variable temperature, we're not able to equilibrate the temperature of the lava. The temperature of lava maybe is usually lower than, maybe lower than that of the apparatus. Okay, or some of the lava became less active. You cannot standardize it. Some of them become more active, some become less active, and then the activity affects the amount of oxygen they use. That could also introduce it. All right, so lava were not fully adjusted. Yeah, they were not adjusted or equilibrated. The lava were at lower temperature than the apparatus, so that could affect it. The lava were less active. Okay, too much. All right, use the data in table 2.1 and fig 2.2. Calculate the volume of oxygen taken up by the, so the volume of oxygen, all right, taken up there. All right, of course they gave us 68. Go back to that. You see the volume of you see the 68 is okay, the distance moved. Okay, so remember that volume of oxygen, volume here is always V, because we're using cylinder. Okay, the tube is a cylindrical tube, pi r square. Okay, height. Okay, yeah, Now what they say for 1 minute, 1 minute. So everything happened in 10 minutes. Everything here divided by everything divided by, okay, by 10. Okay, let's see. What did they give us more information? Fig. Okay, this information they gave us. Fig 2.2 shows section of manometer. This is internal diameter. Okay, so diameter is equal to, right? So diameter over 2 will give us radius. So diameter is 1. So 1 divided by 2 will give us the radius. Okay, and that is 0.5. Okay, so the radius is 0.5. Okay, the distance moved, which in this case is h, is 68. I think so. Check the, okay, moved by the meniscus, 68. So that means that volume, of course, you know what pi squared is. Pi squared, pi, remember pi is a constant, okay? Pi is 3.14. Oh, yeah, 3 point, yep, 3 point what? 14 or 142, okay? Yes, that's pi, 142. So pi is, let's bring on the volume here. So volume is therefore equal to, right? What is pi? 3.142 or 14, okay, times radius. Radius is 0.5 squared, okay, 0.5 squared. So that's radius squared is 0.5. So radius is 0.5, so 0.5 squared, that's radius squared. All right, times the distance moved, which is height there, is 68. Okay, so everything we got here divided by 10, because we measured it in 10 minutes, and we're looking for the volume in 1 minute, so we measure in 10. Okay, so get your calculator. I forgot to tell you to solve this. We should have solved it. Okay, now of course, 0.5 squared is what? What is it? Okay, so that's 0.25 times pi squared. Pi is 3.142. Okay, times what? 68. So that gives you, what does it give you, guys? Hope you're solving this. It gives you 53, right? 53.14. Is that what I'm getting? 53.04414. All right, so divided by 10. Okay, so you just shift the decimal place. Okay, and that will be, it should be 5.3. Yeah, 5.34 approximately. Yeah, 5.34. Okay, of course, millimeter squared per minute, right? Per minute. Yeah, per minute. Okay, all right, let's check what it did. Yeah, volume of this. Okay, good. All right, this is 0.5 raised to power 2, not, okay, this 2 is up here as a superscript, right? And this is not plus, this is divided. Okay, this is divided by 10. So the answer is 5.34. Okay, yeah, but you have to show you're working. So use the answer from F to calculate the respiratory quotient for replicate 5 cows. Okay, yeah, now remember RQ, all right, don't forget RQ is volume of, yeah, okay, let's do it. But pause the video and try it. Pause video and try it. So you know, RQ is what? Volume of CO2, right, produce the volume of CO2, all right, produce all over volume of oxygen used. Okay, it can also be number of moles of each of them. Okay, so volume of CO2, if you check that table, is 3, and we've already calculated volume of oxygen, which is 5.34. Okay, so that was one we calculated. The volume of CO2 is on the table. Go back to pause the video and go back to the table. Okay, so you now say, all right, 3 divided by 5.34, whatever, that gives you 0.56. So RQ value here, it's funny, 0.56. So which substrate was used in this experiment? Was it, looks like lipid, a mixture of lipid and protein? Okay, 0.56. Okay, all right, so that is it. Okay, thank you for watching. So make sure you share this video and let us know what you want, what do you need. Okay, comment, continue to watch. Exam is around the corner. Have a wonderful time. This is Shedro. See you next episode. Bye.